Okay. Thank you for the kind introduction. Today I'm going to share our research work about energy harvesting system. We propose a very simple technique to make energy harvesting system become more efficient. So we know that the battery is not environmental friendly, and the large size of the battery, as you can see in this figure, it will make some wearable device is very hard to implement. And also, the battery also is a bottleneck for IoT device. As you can see in this projection here, in the next 10 years, there will be like a 50 billion IoT device in the market. So if all these IoT devices are powered by the battery, we will need to pay a lot of money to just replace this battery. So instead of using the battery, people introduce the energy harvesting system. Energy harvesting system can collect energy from some ambient source, such as Wi-Fi, radio frequency, solar, and thermal. However, the problem of this energy source is that they are very unreliable. As you can see in these two figures, we get this number from the real energy harvesting system. And you can find that their input power is changing all the time. So the problem is that if the application is running in such kind of device with such kind of power supply, we will suffer a lot of power failure. So the problem of this power failure is that if they happened in the middle of the program execution, all the volatile data will be lost. And the only way to recover is to restart from the beginning. If we have many power failure like this, we have to restart our application again and again. This will take a lot of time. So to handle this issue, people introduce the non-volatile memory and the capacitor for energy harvesting system. So let's see how this works. So energy harvesting system will collect energy and save them inside this capacitor. And when the capacitor is getting fully charged, it will start to run the application by consuming the energy inside the capacitor. When the capacitor runs out of its energy, the energy harvesting system has to stop the running and recharge the capacitor again. And this process will repeat forever until we finish our application. So from the previous page, we found that the energy availability will directly impact the forward progress inside the energy harvesting system. As you can see in this animation, if we have more energy supplied, that means our application can run in maybe for a longer period of time and finish more work. Therefore, it's important that energy efficiency for to improve the performance for energy harvesting system. And many people explore different solutions to improve the energy efficiency. For example, in recent years, people introduced the SRAM cache to the energy harvesting system. So by buffering some reusable data inside the SRAM cache, we can reduce a lot of expensive access to the NVM. These access are very time-consuming and energy-consuming. As reported in the previous work in Michael 2021, sometimes the introduction of SRAM cache can improve the performance by 8.5. This is super promising. But it also introduces some problems. The first problem is that how can we handle this volatile SRAM cache data across the power failure because they are going to lost? And the second question is the leakage power caused by the additional SRAM cache structure. This part will also consume our valuable energy. So for the first challenge, so people usually introduce some checkpoint technique to save this volatile data to the non-volatile NVM, and then when power comes back, it can restore this data. Here we show the architecture of the NVSRAM cache, which is a very typical example of energy harvesting system. The idea of NVSRAM cache is very simple. It just makes a checkpoint right before the power failure. And when power comes back, it can restore everything, including the cache data and the program state, so that the program can restart from the interrupt point. So to achieve this, it relies on a voltage monitor, as you can see in the red cycle here. The voltage monitor will check the capacitor voltage level and to decide a suitable moment to perform our checkpoint. And also, NVS1 cache will will introduce NV backup for its cache, which is called NVS1, as you can see in the right-hand side here. And now let's see how it works. So when the capacitor voltage drops below the backup threshold, its voltage monitor will send a signal to stop the pipeline and to perform the checkpointing. And when the voltage rises above the restoration threshold, the voltage monitor will send another signal to restore the previous checkpointed data so that the program can resume correctly. As for the second challenge, it is the leakage power caused by the SRAM cache structure. This part of energy will waste our harvest energy and will make our performance become worse. In this figure, we show the performance number of NVS1 cache with respect to different cache size. As you can see in this red curve, we found that, of course, the cache size increased and the leakage power also increased. But we found that as the cache size increased from 256 bytes to 2 kilobytes, the performance will increase. But if we further increase our cache size to like 4 kilobytes and 8 kilobytes, we will get a poor performance. This is because many of our valuable energy is wasted by the cache leakage. So the takeaway message here is that the energy harvesting system can only support very small caches. And these small caches can lead to many cache misses problems. So traditionally, people introduce the prefetcher to handle this problem. We know that the prefetcher, you're already familiar with prefetcher, so I'm still going to show an illustration. So in this example, we initially have an empty cache, and the prefetcher will send two requests to get block A and B to the cache, so that when they desired, we can get they quickly from the cache. So, but if we apply the prefetcher to the energy harvesting system, we may not be able to receive the best performance, I would say. Suppose that we already have a prefetch block and bring it inside the cache, but it has not been accessed. At this moment, a power failure happened, which will make all the cache data lost, and this prefetch operation become useless. Let's go back to our previous example to see how this happened. So in previous example, we already get block A and B from the memory to the cache, and block A has its contribution to a cache hit. But unfortunately, after that, we suffer a power failure. And this power failure will erase everything, including the cache block A and B inside the cache. So that means the prefetch operation for the prefetch cache block B is useless. It does not have any contribution, but only purely waste our energy, make our performance become worse. And the worst thing is that in the energy harvesting system, this power failure is very frequent. And that means there are many this kind of useless prefetch operation. They are wasting our energy and wasting our memory bandwidth and finally make our performance become worse. So to handle this issue, in this paper, we introduce our technique IPAX to handle this useless prefetch operation and throttle them when they occurs before a power failure. Let's go back to our previous example again. So in this example, the IPAX find that there might be a power failure in the future. So rather than prefetch block A and B, this time the only prefetch for the block A. And if the same power failure happens, so all the data will be lost. And this time, There is no unused cache block loss upon this power failure because we already throttled the prefetch B by our apex. So the idea of our apex is very simple. It just throttle the prefetch degree. But in our implementation, we still need to address two questions. So the first question is, when should we make the adjustment of the prefetch degree? So the prefetch timing is very important. And if we do the prefetching too late, we may lose many chances to throttle the useless prefetch. And on the other hand, if we do the throttle very early, we can make some useful prefetch operation be throttled and hurt our performance. And the second question is that, how can we address this prefetch degree? So of course, we should set our prefetch degree to the suitable value so to achieve the good performance. And for the first question, it's important to enable our apex in a timely manner. To achieve this, we allow our apex to reuse the voltage monitor inside the energy harvesting system so that it can decide a suitable time to make the adjustment. So in our implementation, we first introduce multiple voltage threshold, and during the system is running, whenever the capacitor voltage drops below a threshold, we will start to, this is the right time to make an adjustment. If the voltage continue to drop to some lower threshold, we should be more aggressive to adjust our prefetch degree to a smaller number. And when power comes back, we will reset our prefetch degree to the normal value, to the initial value, so that the prefetcher can restore its capability. Based on the previous design, now the problem can be translated to how can we determine the suitable voltage threshold. So a very simple solution is that we just empirically select some threshold and fix them during the program execution. But the problem is that this threshold may not always be a good choice during the execution because the energy harvesting quality is changing all the time. Therefore, we introduce an adaptation technique to adjust the voltage threshold based on the throttling rate. You can see in this page that the definition of throttling rate is shown in this equation. Here, the P throttle is the number of prefetch operation that is throttled by our apex. And the P issue here is the number of prefetch has successfully issued to the memory. So let's see how it works. Whenever the energy harvesting system recovers or restored from the power failure, it will first check the throttling rate. If the throttling rate goes too high, that means we may have some over-throttling issues. In this case, we may mistakenly treat some useful prefetch to be useless. In this case, we should decrease our voltage threshold. And on the other hand, if the throttling rate goes too low, we may have some under-throttling issue. Under-throttling issue, and in this case, we may lose many chances to throttle the useless prefetch. So in this case, we will increase our thresholds. And for the second question is, how can we address the prefetch degree based on we have like so many voltage threshold, and our technique, our solution is very simple. That is, as the capacitor voltage drops below a threshold, we will reduce our prefetch degree by half. And on the other hand, we will increase it by 2 times. Let's see a very simple illustration. So initially, the prefetch degree drops below 2 to 1 because of the voltage drop. And if the voltage continues to drop some lower threshold, we will reduce it to 0. And here is another example. So the prefetch degree decrease initially because of the voltage drop, but later the voltage will arise above the voltage threshold. So in this case, we should double it to switch back to the 2. So in our evaluation, we implement our technique on top of the Jianping simulator with MCPad for the energy modeling. We use the mid-bench and the median bench as our benchmark suit, and use the NVS rank cache with a simple stratified prefetcher as our baseline. As for the setting for IPACs, we test it with 2 different settings. In the first setting, we apply IPACs for the data prefetcher only, and in the second setting, we apply IPACs for both data and the instruction prefetcher. As for the power trace, we collect a real radio frequency trace from the real energy harvesting system for all of our simulation. So in this figure, we show the performance of our IPACs compared to the baseline. As you can see in the right-hand side, when we apply the IPACs to the data prefetcher, it gives like a 3.7% improvement to the performance. If we apply the IPACs to both prefetchers, the performance can increase to like 9%. In this figure, we show the number of prefetcher reduction here. On average, IPACs reduce like 7.11% prefetch operations. And for some of the applications, this reduction can be over 15%. And finally, we will show the energy breakdown for IPACs and the baseline system. For each application here, it has 3 bars. And from the left to right, it is the baseline and the IPACs for the data prefetcher and the IPACs for the both prefetchers. So here, so on average, like IPACs reduce like 13.2% energy consumption for the main memory. And for the overload reduction, it reduced like 7.8 of the total energy compared to the baseline. Okay, so in this work, we introduced the IPAC, which can build on top of the existing prefetcher to make the energy harvesting system become more efficiency. And the IPACs can throttle the useless prefetch operation caused by the power failure. And finally, IPACs improve very promising performance and energy efficiency compared to the baseline. And I think this is the end of my talk. And thank you for your listening.